Donaldson theory of C3, please.
Yeah. Yeah, thank you for the invitation to speak here. It's a great honor. So I'll report on joint work with Yukunobu Toda. So first I'll begin with a brief overview of Donaldson-Thomas theory and the categorical Donaldson-Thomas theory. So here a central construction is given by a certain non-commutative resolution of singularities constructed by Špela and Michel. So I'll begin by mentioning it. So they constructed non-commutative resolutions of certain quotient singularities. So V mod G, where G is a reductive group, and V is a symmetric G representation, plus some other conditions. And okay, so maybe I'll give a name to this non-commutative resolution, D. Then they also show the admissibility of D in certain smooth spaces. So D appears as a summand. Maybe, yeah, most important for this talk is that it appears as a summand in a dB of the corresponding stack of this quotient singularity. And I'll say more words about their construction later in the talk. It is also admissible in other resolution of singularities of this quotient singularity, namely the Kerman resolution. And most importantly for people for this categorical Donaldson-Thomas theory, we can use it to define what we call a quasi-BPS category. So use their construction, their NCR maybe. So in Donaldson-Thomas theory, we consider some categories based on coherent sheaves that they categorify structures, more classical structures in enumerative geometry. And in their study, it ended up that they have semiorthogonal decompositions where the summands are these quasi-BPS categories. That I'll also explain. I'll say a few words about where the name comes from. And as I was saying, these quasi-BPS categories are constructed from this non-commutative resolutions of Špela and Michel. They're actually matrix factorizations on these NCRs. So now let me say a few more words about Donaldson-Thomas theory. So this is about virtual counts of sheaves on Calabi-Yau threefolds. And for given a support of sheaves, we get virtual counts of curves on Calabi-Yau threefolds. There are, okay, so one produces this DT invariants, which are certain integers. There are other theories. Also defined using sheaves is Pădurariu-Thomas theory. Defined using moduli of maps to the ambient variety. In this case, Calabi-Yau threefold is Gromov-Witten theory. So Pădurariu-Thomas theory also produces integers. Gromov-Witten produces rational numbers. But underlying these theories, it is expected that there is a more fundamental theory. So this is given, or it's called BPS theory, and it produces BPS invariants. They are also called Gopakumar-Vafa invariants. That determines all this other theory. So determines DT, Romo-Witten, so on. So now in a categorical Donaldson-Thomas theory, we look at categorifications of structures from DT theory. So let's say of DT invariant. So this produces some DT categories. Another direction is to look at whole algebras. So this will be whole algebras associated to Calabi-Yau-3 categories. Introduced by Kontsevich and Soibelman. And these whole algebras are expected, and in some cases are shown to act on these DT categories. Michel also did work on whole algebras, but on the classical whole algebras defined using constructible sheaves. These are defined using coherent sheaves. But his work was about sort of cuspidal elements, and then these BPS spaces, whatever they are also related to cuspidal spaces. So sort of a coherent analog of this construction in a constructible world. Yes, it's a monoidal category. Yes. Okay, so and actually this okay, so both these objects, both DT categories and whole algebras. So they are so this whole algebra is also a monoidal category. Both these categories have semi-orthogonal decompositions, where the summands are these quasi-BPS categories that are defined based on this NCR of Spelai and Michel. And we expect this to be indecomposable in many cases. Okay. And okay, so before I actually move to DT theory of C3, there are basically, well, not only two, but at least two directions of research. So the first one is to study statements for Calabi-Yau-3 folds, which are analogous to known statements about surfaces. So for example, basic example of a moduli of sheaves on a surface is the Hilbert scheme of points on C2. Okay. So this object has been studied a lot. One knows its singular cohomology, its K-theory, things like that. Then what about the Hilbert scheme of points on C3? So C3 is Calabi-Yau, and this is an example of a moduli of sheaves on C3. What does the Donaldson-Thomas theory say about this object? So this is one direction, and this is the one that I'll follow in this talk. The other one, which is more interest to people not working in Donaldson-Thomas theory, is the following. So by this procedure called dimensional reduction, one obtains out of this DT theory for some Calabi-3 categories, one obtains statements, theorems involving more classical objects. Well, yeah, classical spaces. In dimensions 1 or 2. So some examples here. Maybe first due to Halper-Leisner. And then, yeah, the statements do not involve Calabi-3 categories. They involve moduli of sheaves on spaces of dimension 1 or 2, and dbco on such spaces. So the first example due to Halper-Leisner is derived equivalence of dbco of moduli of semi-stable sheaves on K3 surface. So here, this moduli have the same support, but one varies the stability condition. Then for dimension 1, there is work of Toda. So he constructed semi-orthogonal decompositions of dbco of quote schemes on curves. And he also deduced semi-orthogonal decompositions for dbco of Brill-Noether loci on curves, and also for dbco, particular case, it's dbco for symmetric powers of curve. And then this whole algebras, this categorical whole algebras, they are categorification of quantum affine algebras. So also using this Donaldson-Thomas philosophy and dimensional reduction, we also show some structured theorems. So either semi-orthogonal decomposition for the categorical whole algebra or PBW theorems for K-theoretic whole algebras. So structured theorems for, maybe I'll call them just this pre-projective whole algebras. Okay, so the plan is to talk about the Hilbert schemes of points on C3. But before we do that, let's see what results are known about the Hilbert schemes of points on C2 and what we're trying to generalize. So first, we'll do Hilbert schemes of points on C2. And the first questions would be about the topology of this space. Well, so we know something about the geometry. So this is smooth and connected space. The first question about the topology would be, what is its Euler characteristic? So we can compute this using localization. So there is a two-dimensional torus scaling C2, and this action extends to an action on the Hilbert schemes of points on C2. And the T-fixed loci are end up being points. And so here we regard the Hilbert scheme of points as parameterizing ideals. Maybe I'll write here. So this is ideals in polynomial ring or two variables of colength B. And the T-fixed points will correspond to monomial ideals. And I'll draw here. And out of such a monomial ideal, we can obtain a partition of D. So what we do is we look at the complement of pairs ij such that xi, yj is in the ideal, fixed ideal. So this complement will provide a partition of D. So the Euler characteristic of Hilbert C2D ends up being P2D. So this is my notation for number of partitions of D. And then actually this localization technique and the Bielaniki-Birol decomposition provide a cellular decomposition of Hilbert C2D. One can compute the number of cells of a given dimension. So this also gives us the Betti numbers. More immediate is to find the Grothendieck group. So K naught of Hilbert C2D is the number of cells. So it will be Z power P2D. And there is also a derived equivalence underlying this equality. So this is the Bridgeland-King-Reid Haiman theorem. So they prove that dBco of Hilbert C2D is derived equivalent to dBco, maybe right here, of the following orbifold. So we take the affine plane, raise it to the D power, and then we let sigma D act by permuting the factors. So we get an orbifold, which is derived equivalent to the Hilbert schemes of points on C2. Okay. So we would like to do the same thing for Hilbert C3D. So first, it will be, find sort of its Euler characteristic. What can we say about the Betti numbers of Hilbert C3D? What can we say about K-theory or dBco on Hilbert C3D? Okay. So the main difficulty here is that the spaces are now very singular, or D at least 4, and they have multiple irreducible components. We do not know their dimensions. So in particular, it will be, or it is very hard to find the Betti numbers. And also, the Grothendieck group is not well behaved. Also, the category of coherent sheaves. However, the Euler characteristic computation is similar to the one above. So let's do that. So chi of Hilbert C3D. Once again, we can use a localization for a three-dimensional torus now, acting on C3. And the fixed loci once again correspond to monomial ideals. In polynomial ring on three variables of co-length D. And looking at the complement in the first octant of monomials which are in this T fixed loci, we obtain a three-dimensional partition of D. So this Euler characteristic will be this P3D. So this is my notation for 3D partitions of D. Okay. So as I was saying, this Betti numbers are hard to compute. We don't even know the dimensions of the irreducible components of Hilbert C3D. And here is where Donaldson-Thomas theory comes into play. So Donaldson-Thomas theory tells us to look at a replacement of the constant sheaf Q on Hilbert C3D. This replacement is a certain perverse sheaf, and the computations of the hypercohomology of that perverse sheaf are easier to compute, and we obtain analogous results to the ones in dimension 2. So this is what I'll explain next. So DT theory. Okay, so it tells us. Okay, so now this is a central fact in DT theory. That will explain how to construct this perverse sheaves. And this fact says that if you have moduli of sheaves, so they should be compactly supported and semi-stable for example, Giesinger stability condition, moduli of sheaves on smooth complex Calabi-Yau threefold, okay, is locally, analytically of this form, is the critical locus of a regular function on a smooth space. So itself, it is not smooth, it actually has bad singularities. Already for this sort of simplest example of a moduli of sheaves on a Calabi-Yau threefold, namely Hilbert C3D, is very singular, but it's, yeah, just to write a math formula. So it's the critical locus of a regular function on a smooth space X. So from here, we can get a perverse sheaf on the, so there is an actual perverse sheaf, namely the vanishing cycle sheaf. And one can glue this vanishing cycle sheaf. So this is work of Joyce and his collaborators. And then in DT theory, one studies the obtained perverse sheaves and their hypercohomology. So maybe, so now I can, okay, so I'll explain this construction for Hilbert C3 next. Okay, so this parameterizes quotient. So now we move from ideal to quotient. It will be quotient of polynomial ring in free variables. So V is a vector space of dimension D. Okay. And let's see how we can write this data using some linear maps. So first we have a lowercase v. This is an element of the vector space, which is the image of 1 under this surjection. And then x, y, and z also give us endomorphisms of v. Okay, so uppercase x corresponds to the action of the generator x, lowercase x. So the points are given by tuplets v and x, y, z in v times GLV plus 3 with the following conditions. So the first one that says that this map is a surjection is that lowercase v generates the vector space v under the action of this linear maps. So I'll write this as follows. And the second condition is that x, y, and z, these endomorphisms, commute because they are constructed from the image of generators of a polynomial algebra. This is. Okay. This second condition is the one that introduces singularities. Okay, so let's eliminate it. And then we consider the non-commutative Hilbert scheme of d points. So this will parameterize tuplets v, x, y, z in v times GLV plus 3. And we just keep the first condition. So lowercase v generates the vector space under the action of x, y, and z. Okay. So now this is a GAT quotient of this particular vector space by GLV, and it ends up being a smooth space. And now to realize the Hilbert scheme of points, we need to add this condition that x, y, and z pairwise commute. So to do this, we write, so this sort of central fact in DT theory tells us we should write this as the critical locus of a function. And this function is the trace of x times the commutator of yz. Okay. Okay, so I'll write this as w. So the critical locus of w is taking the partial derivatives with respect to the coordinates of x. We see that y and z have to commute. And then permuting this relation, we get that x, y, and z pairwise commute. So the critical locus will be the Hilbert scheme of points on C3. Okay. So now we can consider the vanishing cycle sheaf. So this phi will be phi. So this is the vanishing cycle functor for this regular function applied to the IC sheaf. So this is a certain shift of the constant sheaf on this smooth space. So in DT theory, now one studies the hypercohomology of this sheaf. So the first thing to do is to take its Euler characteristic. So then one recovers the classical DT invariants that were introduced initially using virtual fundamental classes. This. So we managed to compute actually the Euler characteristic of Hilbert C3D. Now we are doing this Pervers sheaf cohomology instead. The first question is this answer related to the first one that we got? So does it have to do with the number of 3D partitions of D? And this is the answer is yes. It's a theorem of Bergh and Van that says the dTd is, now we'll also have a sign, -1 to the D, that actually comes from this shift, from the IC sheaf, times P3D. So up to a sign, we recover the initial answer, the computation of the other characteristic of Hilbert schemes of points on C3. But the advantage is that now one can also compute the individual homology spaces of Hilbert C3 D pi. But this is work of Berendt, Bryan, Chandroy, and Davison. So this is a better behaved theory. So now, inspired by this construction, we would like to look at the K-theory of Hilbert C3D. No, yes. Yeah, so the whole structure is of pure Tate type. So, as I was saying, we will not just look at the quadratic group of coherent sheaves on this space. We will look at a different category. So this DT category is the matrix factorization category on N Hilbert D, on the non-commutative Hilbert scheme for the regular function W. So, so here we have some flexibility and consider this matrix factorization. We can also take graded matrix factorization. We can also take equivariant matrix factorizations. So the objects here are tuplets AB with maps alpha beta as follows, such that AB are coherent sheaves on N Hilbert D, or vector bundles if you want, such that the compositions alpha beta and beta alpha are both multiplication by W. And why are we looking at matrix factorizations? So the reason is the theorem of Efimov that says that the periodic cyclic homology of matrix factorizations recovers the Z-mod 2 periodic Z-mod 2 periodization of vanishing cohomology. So in particular, this theorem of Efimov implies the following thing. So it implies that if you take the Euler characteristic of periodic cyclic homology on these DT categories, so this will be the dimension of HP naught minus the dimension of HP1. One recovers the DT invariant. So also by Berendt Van Teki, we know the answer is -1 to the D P3D. So now I can be a little more precise about the questions we're interested in. So looking back at the Hilbert schemes of points on C2, dBco of that space is indecomposable. The first question would be, is this category indecomposable? So 1. And if not, find the semiorthogonal decomposition with indecomposable summons. And even more, looking back at the Hilbert schemes of points on C2, we saw that dBco of Hilbert C2D is derived equivalent to dBco of the orbifold C2D mod sigma D. So maybe, so the dream here would be that this indecomposable summons have to do, okay, so are related to the analogous quotient for C3. So C3D mod sigma D. This would be a first problem. The second problem is compute the Grothendieck group of these categories. And well, a first basic question would be, do you recover something resembling this classical computation, this numerical computation of Berendt-Van-Teke? Or find analog. Okay, so now the summands are these quasi-BPS categories. So I'll explain a particular case of this construction of Spela and Michel. So the singularity here will be GLV plus 3 mod GLV. So where V had dimension D. So if you want to think, if you like quivers, this is the core space of a 3-loop quiver. So they constructed twisted NCRs, MDW. So this W is an integer. Okay, so they are generated by certain vector bundles. So generated by okay. So I should have said that this is a subcategory inside dB of XD. So this is the stack. Maybe right here. So this XD is the stack of representations of this quiver. So it's GLD plus 3 mod GLD. So it's generated by vector bundles. So this chi is a dominant weight of GLD such that chi is in a certain polytope inside the weight lattice of this reductive group GLD. So such that chi plus rho, so rho is half the sum of positive weights of GLD, is in this polytope that's given by a Minkowski sum. So it's 3/2 sum of the intervals 0 to beta I minus beta j. So here, this beta I are sort of simple roots. So beta 1 up to beta d. And the W appears that sure, if we stop here, then chi, the dominant weight will be forced to have the sum of coefficients 0 to allow variable sum of coefficients. So we need to take this shift W over D, sum of beta. What is remarkable about this construction is that, as I said in the beginning, it's admissible. It's not just a subcategory, but it's also admissible in a dB of the stack. But also in the last 10 years or so, there had been a lot of development in this semiorthogonal decompositions of smooth stack using weight type structures. So this work of Halper-Leisner. Ballard, Favero, Katsarkov. Spela and Michel. And what is remarkable is that in the symmetric case, so this GLV is a symmetric representation of the reductive group GLV. This construction, this categories are as small as possible given this weight technology. So also these BPS spaces, so as I said, they are like the most basic numerical invariants. And in cohomology, these BPS spaces should generate and indeed they generate the hypercohomology of this Donaldson-Thomas spaces. So in the categorical world, we also like some admissible subcategories inside the stacks, which are as small as possible, but using the whole product, they produce semi-orthogonal decompositions of these categories. And this is precisely what these categories of Špela and Michel do. So now these quasi-BPS categories SW, they will be matrix factorization. So they are inside MV of the stack XD, W, and they are tuplets such that alpha beta and beta alpha are multiplication by W. So now, okay, so the first theorem. We construct semi-orthogonal decomposition of these DT categories. So yeah, just to repeat, we also expect these categories to be indecomposable. We don't know how to show that. So the semi-orthogonal decomposition is using the whole product as DI WI. And let's see, what are the weights WI that appear here? So first, the DIs will have to be a partition of D. And then if we define VI to be a weight, the following weight, so it's WI minus DI times DJ, where J is greater than 1, minus DJ, where J is less than I. Then we have the following Harder-Narasimhan type condition. We have that V1 over D1 is less than VK over DK. And all the slopes are inside the interval 0, 1. So actually this condition here looks nicer under dimensional reduction than after applying a causal equivalence. In any case, so this is the first result. So the first question was whether DT is indecomposable. The answer is no. And we expect these categories to be indecomposable, as I was saying. And then so this SDW, there are these quasi-BPS categories. So they are subcategories of this category of matrix factorization, where the summands are tuplets as follows. Oh, yeah, sorry, I didn't say. Thanks a lot. Where A, B are in this MDW category, in this non-commutative resolution. So you just take dominant weights that are in a specified polytope in the weight lattice. Yes, thanks. So now for the second question. We see that we have to find, by the first theorem, we need only to study the Grothendieck group of quasi-BPS categories. Actually, this ends up being difficult. So there are multiple possibilities here to simplify the problem. Either we look at topological K-theory, or even simpler, we look at equivariant K-theory, and then we localize. So this is what we do. So we take a two-dimensional torus, fixing the product XYZ. So this is the Calabi-Yau torus of C3. And okay, so I'll introduce some notation. So this is K naught of BT. and F is the fraction field. Okay. So the simpler problem is to, yeah, maybe I'll just write the theorem here. Is to look at the dimensions of the localized T equivariant K theory of quasi-BPS category. So SDW. Like this. And also by, oh, yeah, the second part of one, we hope that the summands are related to C3D mod sigma D. So for example, to matrix factorization on this orbifold and regular function 0. Well, if that would be the case, a first consequence will be some numerical K-theory computations. So this will have to do with the dimensions of the space will have to do with number of partitions of these. So just 2 classical partitions, not 3D partitions. And indeed, this ends up being P2N, where N is the greatest common divisor of the NW. So maybe the hope would be that SD naught has to do with matrix factorizations on C3D mod sigma D. And then putting this together with theorem 1, we get a corollary that the dimension of this localized equivariant K theory. Okay, so if one does the computation, actually recovers P3D. So we recover, or we find an analog in K theory of this Bergh-Van theorem. Okay, that's all.